In each of the three triangles on this page of your notes, sides A and B are the same length. We can use the Pythagorean theorem to find the length of side C in the right triangle, but how do we find the length of side C in the acute and obtuse triangles? So let's assume, for the sake of argument, that in each of these triangles that side A and side B and angle C are known quantities. So if we knew side A and side B and angle C was 90 degrees, then we can use the Pythagorean theorem. A squared plus B squared equals C squared. But when we go to triangle 2, and we know, once again, let's say we know A and we know B and we know sine of C, or we know angle C, we notice here that angle C is less than 90 degrees. So given that A and B are the same length, then side C must be less than side C was in the first triangle. So how do we know how much less it is, and how do we figure this out? So there is a way that you already know to figure out side C, but it's kind of a multi-step process. If we were to drop down an altitude here, because I know side A and side C, I could use the sine function, side A and angle C, I could use the sine function to find this vertical side. Once I know this vertical side and I also know side A, then I could also find this little horizontal side. Then I could figure out what this other section of the base is over here, and then knowing these two sides, the vertical side and this other piece here, I could figure out what C is. So there is a roundabout way of getting there, but what we're going to do is use that roundabout way to derive a formula that is going to be a little more efficient in figuring out what side C is, and it's called the law of cosines. So let's start out by labeling some of these pieces of right triangles that we know. I'm going to say that the distance from angle C to the altitude here is x, and I'm going to call this altitude y. And since this distance from C to the altitude is x, then the remainder of the base then must be b minus x. So now I have two right triangles with all three sides labeled, and I'm going to apply the Pythagorean theorem to both of them. So on the first, the one to the left, I have a squared plus x squared equals, no, sorry, that's wrong. I'm sorry, I have x squared plus y squared equals a squared. And in the second triangle, I have y squared plus b minus x squared is equal to c squared. Now once again, my goal is to be able to figure out C by only knowing side A, side B, and angle C. So I'm going to have to do some substitutions. First of all, you notice that I could solve the first equation for y squared and substitute it into the second equation. So I can say here that y squared is equal to a squared minus x squared, and substitute that in here. So that would give me then a squared minus x squared plus the quantity b minus x squared equals c squared. Now I'm going to multiply out b minus x squared, and just to remind you what b minus x squared is, I'm going to just kind of go over, I guess right here, b minus x times b minus x is b squared minus bx minus bx plus x squared, because a negative times a negative is a positive. So this turns out to be a squared minus x squared plus b squared minus 2bx plus x squared, and then that whole thing equal to c squared. I'd like you to get to the point where you can just see b minus x, the quantity squared, and recognize that you're squaring the first term, you're squaring the last term, and that the middle term is just two of those multiplied together. So b times negative x twice, because that happens twice when you use FOIL. Now a nice thing happens here. We have a negative x squared and a positive x squared. So this simplifies to a squared plus b squared minus 2bx equals c squared. So the a squared plus b squared equals c squared part is just the Pythagorean theorem. This little quantity right here tells me how much side C is smaller than it used to be. Now, x is still not one of my given quantities. My given quantity is angle C, side A, and side B. So can I write x in terms of my given quantity? Well, yes, I can, because I know SOHCAHTOA, and I can say cosine of angle C is x over A. So I'm going to go over here and write that. Cosine of C is equal to x over A. So solving that for x, A times cosine C is equal to x. So I'm going to substitute that in here, and then I'm going to end up with a squared plus b squared minus 2b times a cosine c equals c squared. Now just a little rearranging and we'll have the law of cosines, because notice now everything on the left hand side of the equation is in terms of things I know. I've been given angle A, or side A, side B, angle C. Everything or those are all known quantities, and I can find C, side C, using those pieces of information. So C squared equals A squared plus B squared minus 2, and I'm going to write this as AB instead of BA, AB cosine of C. And this is known as the law of cosines. Now, a couple of things I want to point out to help you remember this law is that sides A and B show up in two different places, here and here. So the A squared and B squared that's over here, then the A and B is in this subtracted portion also. And then we have side C and angle C are on opposite sides of the equation. So that's always going to be true. Whatever this side is, then that's going to be this angle over here. Now, one other thing to point out is the difference between when my unknown angle C is an acute angle and when my unknown angle C is an obtuse angle. So let me kind of bring this down here. So let's say in this case my angle C here is obtuse, and this is A and this is B. So I want you to think about the difference in this term. We said this is the quantity that we subtracted to see how much smaller C was than its original hypotenuse length in the first triangle. Now C has gotten bigger than, because now C is an angle bigger than 90, so side C is even bigger than it was before. So basically I'm going to have to add something here. So how does this formula both act as a subtractor and an adder to that side C? Let's think about that. When angle C is in the interval 0 to 90, and actually I should say it's not actually equal to 0 to 90, but it's in between, it's basically in quadrant 1, then cosine of C is positive. It's a positive trig value. Think about quadrant 1 angle, quadrant, versus a quadrant 2 angle. Cosine is positive over here. Cosine is negative in quadrant 2. So when angle C is in the interval 90 to 180, then cosine C is negative. It is a negative trig value here. So when I do negative 2AB cosine of C, and cosine is negative, then the whole thing becomes positive. So this quantity that is subtracted, I'm subtracting a negative number. It'd be minus 2 times A times B times this negative number. So when I'm subtracting a negative number, it turns out that I'm adding something then to this side. And then if angle C is equal to 90, cosine of 90 is equal to 0. So negative 2AB, bring that up a little, cosine of C is equal to negative 2AB times 0, so it's 0. And that means that the law of cosines then just becomes the Pythagorean theorem. So the law of cosines is actually a special case of the Pythagorean theorem. I'll just summarize that. So when C equals 90, the law of cosines becomes the Pythagorean theorem. So you've actually been using the Pythagorean, or the law of cosines, for many years, and you just didn't know it. It's just the simplest version of it. Okay, in the next video, then we'll apply this law, the law of cosines, to some different triangles with different letters in them and see how this all works out with the computations.